This video describes two new procedures added to StatGraphics Centurion version 17 for performing Kriging. Kriging is a methodology that's commonly used in geostatistics to predict the value of a random variable over a spatial region. Given a set of measurements at locations in that region, Kriging creates a map of the predicted value throughout the region. It's widely used in environmental science, in mining, in soil science, in hydrogeology, and in many other areas. StatGraphics version 17 contains two procedures for Kriging. The first is a Kriging statlet. The statlet is used to visualize the data, to select the proper model, and to help set analysis parameters. The full-blown Kriging analysis then creates a full set of both tables and graphs. The sample data we're going to look at was collected at the Rothamsted Agricultural Research Center around Brooms Barn. Soil samples were obtained at 435 locations throughout a 77-hectare field. Measurements were made of the amount of exchangeable potassium, the pH, and the available phosphorus in each soil sample. I've loaded the data into the StatGraphics data sheet. Each row shows the measurements at a single location throughout the field. The columns east and north are the distances in meters from the southwest corner of the field. The columns K, pH, and P are the measured data. The X1 boundary and X2 boundary columns are the vertices of a polygon that defines the region over which predictions are desired. I'll now select Statlets from the main menu and choose Kriging. On the Data Input dialog box, I'm going to type in log of K as the variable that I want to predict. The X1 and X2 columns are used to show the location of each of the measurements. The X1 boundary and X2 boundary columns go into these respective fields. When I press OK, a scatter plot will come up, a three-dimensional scatter plot, showing the measurements throughout the field. You can see there's quite a bit of variation. If I click on the Display in 2D button, you can see that the measurements were taken over roughly a rectangular grid. Although there were certain areas, swampy areas, areas where a structure was located and where there was a road, where measurements could not be taken. The first step in applying Kriging is to estimate the variogram. The variogram describes the spatial dependence throughout the region. In particular, it estimates the variance, gamma sub h, between the response at two locations in the region, two locations separated by a distance h. We'll make one simplifying assumption. We'll assume that the variance depends only on the distance h and not on the position of the two locations or the direction between them. Variograms have three characteristics. One is the nugget. That's the height of the variogram at the origin, h equals 0. The second is a sill, which is the asymptotic limit that the variogram approaches as the distance h increases. The third is the range. That's the distance at which the difference between the variogram and the sill becomes negligible. We will examine the empirical variogram, the variogram estimated from the data, to select a good mathematical model. I'll now return to the statlet and click on Variogram. This shows you a plot of the estimated variance at different lag distances. as the distance between two locations increases, as expected, the variance goes up. You can see that it begins at a certain distance above 0 at the origin. That's the nugget. It rises and then reaches a fairly flat asymptotic level at a certain point. The asymptotic level is the sill. The distance at which it approaches the sill is the range. Now, if you go out to very large lags, you'll see that the variance starts to go up again. But at those large lags, the estimates are quite unreliable because there are very few pairs of points separated by that distance. Looking at the empirical variogram, it appears that it's reached an asymptotic value by about 600 meters. Therefore, I'm going to go up to the Statlet toolbar and reduce the maximum lag at which the models are being fit to 600. Currently, it's fitting an exponential model, which gives an R² of about 98.58%. We can do even a little better if we change the model to spherical. That gives an R² of about 99.8% and a very good fit to the empirical data. It's now time for step 2. During step 2, we'll predict the response at many locations X throughout the region. At each location, we'll use a weighted average of the n nearest neighbors. That is, the n nearest locations where data was obtained. The weights depend on the estimated variogram. Exactly how they're calculated is beyond the scope of this video. There are several quantities we can select. The first is the increment. That's the distance between consecutive locations at which we make predictions. The second is the maximum radius. That's the maximum distance from any location X that we'll consider when we select the nearest neighbors. Finally, we can specify the maximum points and minimum points. That puts limits on the number of nearest neighbors, a minimum number that could be included and a maximum number that could be included when we make our predictions. I'll now return to the Statlet and select Response Map. This will show me through a color gradient the predicted values of log potassium throughout the region. It's color-coded. Dark blue represents a low value, dark red represents a high value. There are controls on the toolbar to change the increment, the max radius, the max points, the min points. You'll see as I move these controls that the parameters have little effect on the predictions. The increment does make it a little bit more detailed, but it's clear that there's one hotspot and several fairly low areas. I can also create a three-dimensional representation if I uncheck the box that says Display in 2D. Now it will display the predicted values as a gradient surface plot. I'll rotate it a little so you can see the high areas and the low areas a little better. One more plot is quite interesting. I'll go back to the toolbar again and this time select Variance Map. What you'll see is the estimated variance of the predictions. You can see that the estimated variance is fairly constant in areas where I had a lot of data. Where the data is missing and along the edges of the experimental region where I don't get as many pairs of points in my empirical variogram, the estimated variance of the predictions is somewhat larger. When I'm happy with the model, I can then run the full-blown Kriging procedure by selecting Describe from the main menu and then Geospatial Data, Kriging. The Data Input dialog box is the same as for the statlet. I'll put in log of k for the y variable. I'll put in east and north for the locations. And I'll put in x1 boundary and x2 boundary to define the region. It'll now give me a choice of tables and graphs that I can display. The table, the Kriging table, is the place where I can actually see a table of predictions. When I press OK, it will perform the Kriging and the estimated results appear down in this table. In this analysis, you set options by pushing the right mouse button and selecting Analysis Options. To get the same results that I was seeing in the statlet, I need to set the same parameters, which means I need to change the maximum lag distance to 600 for the variogram, make the increment 32, and set the model to spherical. When I press OK, I'll see tabulated results that match the statlet.